Hello Calc 3 and welcome back to another video. In this video we'll be covering section 15.7, just the second half now, on triple integrals in spherical coordinates. So remember in the last video we focused on evaluating integrals over regions that were given in cylindrical coordinates, as well as functions that were given in cylindrical coordinates. In this video we introduce a new type of coordinate system that you haven't seen before, called spherical coordinates, and then we're going to build up the triple integral for spherical coordinates, just like we've done before. So spherical coordinates locate points in space by using two angles and one distance. So if you think back to cylindrical coordinates from the last video, we had a coordinate r, a coordinate theta, and a coordinate z. And theta represented an angle in the xy plane, and r and z both represented distances. R represented the distance from the origin in the xy plane, and z represented the vertical distance from the xy plane to the point. But for spherical coordinates, we have two angles and only one distance. So we represent a point P as an ordered triple. Those variables there are rho, phi, and theta. So the rho looks like a P, but it is not a P. Where rho is the distance from the point P to the origin. Phi is the angle that the vector from the origin to the point P makes with the positive z-axis. And note that phi is always going to be between 0 and pi. And theta is the angle from cylindrical coordinates. So theta is going to be the angle in the xy plane between the positive x-axis and the projection of OP down onto the xy plane. So you can see all of this information here in the diagram that I have. Notice that we have r drawn into the diagram, which is the length of the projection of the vector from the origin to P down on the xy plane. We also have the angle theta, which represents the angle between that projection r and the positive x-axis. You can see phi is the angle between the vector from the origin to P and the positive z-axis, and then we have rho, which is the distance from the origin to the point P. So again, notice that phi is always going to be between 0 and pi, and we can view theta as the angle in the xy plane between the x-axis and the projection of the vector from the origin to P down onto the plane. And also note by a little bit of a trigonometric argument, we have that the coordinate z, the rectangular coordinate z, is equal to rho times cosine of phi. So if you want to see why that's the case, then you can just pause the video and think about it for a little bit. And this will help us convert between rectangular, cylindrical, and spherical coordinates. And this moves us down into some equations that we now have that relate to these three different coordinate systems: spherical, Cartesian, and cylindrical. So we still have the relations between cylindrical coordinates and rectangular coordinates, and we can just add in a few more to relate spherical coordinates and cylindrical coordinates, and that'll give us a relation between Cartesian coordinates as well. So we have that r is going to be equal to rho times sine phi. Again, this is just a little bit of a trigonometric argument. You can even see it in the diagram up above. So again, if you want to see why that's the case, you can pause the video and look at that diagram. We still have that x is equal to r times cosine of theta. So that's from cylindrical coordinates. And then using the fact that r is equal to rho times sine phi, we can say that x is equal to rho times sine phi times cosine theta. We also have that z is equal to rho times cosine phi, which again is given up in the diagram. And we still have that y is equal to r times sine theta from cylindrical coordinates. And now using the fact that r is equal to rho times sine phi, we end up with y is equal to rho times sine phi times sine theta. And then finally, one more relation that's a little bit unique to spherical coordinates, we have that rho is equal to the square root of x squared plus y squared plus z squared. And this is basically by definition, because the square root of x squared plus y squared plus z squared is the distance in Cartesian coordinates from the origin to the point P. And we've said that rho is defined to be the distance from the point P to the origin. And we still have that r squared is equal to x squared plus y squared, so we can substitute the x squared plus y squared inside of the square root, and we get the square root of r squared plus z squared. So these are important equations. I think I have a note at the end of the video, but at the end of section 15.7, the book actually has one box that lists the relations between all the different coordinate systems. And that's probably going to be a helpful resource for you when you're doing homework or completing quizzes or tests, so I would check that out. Okay, so let's move on to a couple of examples where we're getting used to the spherical coordinate system before we move on to integration. So in this first example, we want to find a spherical coordinate equation for the sphere given by x squared plus y squared plus z minus 1 squared is equal to 1. So here we have an equation in Cartesian coordinates, and we want to convert it to spherical coordinates. Okay, well, the first thing that I did, there's probably multiple ways to go about doing this, but you can take that z minus 1 squared term and just expand it. So we get an x squared plus y squared plus z squared minus 2z plus 1 is equal to 1. The 1's will cancel from both sides. So we have x squared plus y squared plus z squared minus 2z is equal to 0. And now we can do a bunch of substitutions based on these rules that we have above. So we know that rho is equal to the square root of x squared plus y squared plus z squared, which means that rho squared will equal x squared plus y squared plus z squared without the square roots. And so we can substitute rho squared in for this x squared plus y squared plus z squared here. And that'll give us rho squared minus 2z is equal to 0. But we also have an expression for z in spherical coordinates as well. We know that z is equal to rho times cosine of phi. So ultimately we get rho squared minus 2 rho cosine phi is equal to 0. And we can make that look a little bit nicer by just dividing rho from each side here. And we get rho is equal to 2 times cosine phi. And we should note here that this is for rho greater than 0 because we did have to divide by rho from each side of that equation. Okay, and one more example where we find a spherical coordinate equation for an equation given in rectangular coordinates or Cartesian coordinates. So this time we have a cone given by z equals the square root of x squared plus y squared. Well, remember, x squared plus y squared is going to equal r squared. That's an equation that we have for polar coordinates. And so we can rewrite z equals the square root of x squared plus y squared as z equals the square root of r squared. And we're assuming that r is greater than 0, so that allows us to say that z is just equal to r. And now that we have it in cylindrical coordinates here, actually, we can take the equation in cylindrical coordinates and convert it further into spherical coordinates. So we still have from the equations above that r is equal to rho times sine phi, and we also have that z is equal to rho times cosine phi. And so substituting both of these into the equation, we have that rho times cosine phi is equal to rho times sine phi. And we can divide rho from both sides, assuming that rho is greater than 0. And that allows us to say that cosine phi is equal to sine phi. But the only time that cosine phi is equal to sine phi, where phi is between 0 and pi, is going to be when phi is equal to pi over 4. So if you want to convince yourself of that fact, draw a unit circle and see when cosine of an angle is equal to sine of an angle, when the angle has to be between 0 and pi, and you'll find that that only happens when phi is equal to pi over 4. So ultimately the equation for the cone in spherical coordinates then becomes just phi is equal to pi over 4. And now that we have both of those examples down, here are a few more interpretations of equations in spherical coordinates that have constant coordinate value. So if we have some constant rho as our equation, so rho is equal to 4, for example, this is going to give us a sphere that's centered at the origin of radius 4, because it means that all of the points on the surface are going to have distance 4 from the origin, which is by definition a sphere of radius 4. If we have phi is equal to pi over 4, for example, which is what we just got in the example above, then this is going to be a cone that opens upwards from the origin that makes an angle of pi over 4 radians with the positive z-axis, and I have a picture for that here. The reason is that because we just have that phi is equal to pi over 4, rho is going to be unbounded. Rho can be anywhere between 0 and infinity, so the cone is going to extend out forever. And because we don't have any bounds on theta, theta is going to go all the way around the z-axis. And so we end up, you can kind of think about it as taking that ray, phi equals pi over 4, and rotating that ray around the z-axis, and you end up with a cone. And then we also have equations where theta is constant. So let's say that theta is equal to pi over 3, for example. Then this ends up being a half plane that's hinged along the z-axis, making an angle of pi over 3 radians with the positive x-axis. So again, theta equals pi over 3 means that I can draw a ray starting at the origin in the xy plane that makes an angle of pi over 3 with the x-axis. So hopefully you can see that inside of the diagram that I drew. But rho is not going to be bounded, meaning that the ray can go off infinitely. And we also have that phi is not bounded. So you can think about the fact that phi is not bounded means that you also have rays that look like this, all the way from 0 to pi. And so if you think about all of these rays that can extend out as far as you want, because rho isn't going to be bounded, rho is free here, then you can think about these rows tracing out that whole half plane. So nothing over in this region is going to be hit, but we are going to hit all of the points inside of this plane that makes an angle of pi over 3 with the x-axis. So hopefully at this point you're feeling a little bit more comfortable with spherical coordinates, and the goal now is to move into integration using spherical coordinates. So just like we've done in the previous sections, we're now going to build up the notion of the triple integral for spherical coordinates specifically. So again, we're going to have some region D in three-dimensional space, and we can partition that region D into what we will call spherical wedges. And we can partition it into n of these spherical wedges. So if you look over at the diagram that is on the left here, the wedge, or the spherical wedge that I'm talking about, is just the little red block that's showing up right here. So not the other stuff that's showing up in a little bit of a darker tint of red, but just that block. And we can number all of these wedges from 1 to n inside of our partition, and the size of all of the wedges is going to be given by the change in rho for the wedge, the change in theta for the wedge, and the change in phi for the wedge, as you would probably expect. And we can also pick points, rho sub k, phi sub k, and theta sub k within each of the n wedges. And unlike what we did for using polar coordinates, I'm not going to give the derivation of the volume of each of these wedges here, but you can calculate it, and it ends up being the case that the volume of each of these wedges is given by rho sub k squared times sine phi sub k times delta rho sub k times delta phi sub k times delta theta sub k. So the important thing to note here is we would expect these things to show up inside of our integral, But just like when we were taking area with polar coordinates, we had an extra r that showed up. This time we have this extra rho and sine, or rho squared and sine phi that are showing up because we're using spherical coordinates. So because the volume is given as this equation here, then we have that the Riemann sums are going to look like S sub n is still equal to the sum of all of the volumes of the n different wedges, which is going to be equal to, oh, actually this should not be volume, this should be f of rho sub k, phi sub k, theta sub k, times the volume, which I just forgot to put in there. But that'll give us the sum from k equals 1 to n of f of rho sub k, phi sub k, theta sub k times rho sub k squared times sine phi sub k, and then times all of these deltas that are still latched on the end here. And the importance of this is that the triple integral of f of rho phi theta, so this is just some function given in spherical coordinates over a region D, is still going to be defined as the limit as n goes to infinity of these Riemann sums, these S sub n's here, and that is going to be equal to the triple integral of f of rho phi theta times rho squared times sine phi. So we have this that gets carried inside of here, d rho, d phi, d theta over the region D. So again, just like we had an r that got pulled in when we talked about areas using polar coordinates, here we have a rho squared times sine phi that's getting pulled into the integral. So you have to make sure to account for that when you integrate. Okay, so again, just like we've done in other videos, now the goal is to talk about finding the limits of integration if we want to integrate in spherical coordinates. So to evaluate the triple integral of f of rho phi theta over some region D in space in spherical coordinates, where we are integrating first with respect to rho, and then with respect to phi, and finally with respect to theta, we're going to take the following steps in this order. So the first thing, just like we always do, regardless of how you're integrating, you're going to sketch the region D in space along with its projection on the xy plane. And this is just to give us some visualizations that we can kind of pick out what the limits of integration are going to be for our three different variables. So you can see that we have our region D in space here, and then we also have the projection of that region down onto the plane that's given by R. And now we're going to move on to finding the rho limits of integration because we are integrating with respect to rho first. So to do that, we can start rays at the origin that go out through our region D. And the question is, along what surfaces are these rays going to enter and exit the region D? So if you look up at the diagram, the ray, or an example of one of these rays would be the ray given by M here. So it starts at the origin, it's going out from the origin up through the region D, and you can see that it's entering the region D along this surface rho equals g sub 1 of phi theta, and it's exiting the region D along the surface rho equals g sub 2 of phi theta. And these are going to provide the upper and lower limits of integration for rho, as you would probably expect. And now we want to find the phi limits of integration. So this is going to be a little bit different than normal, than it was for cylindrical coordinates. It'll probably feel a little bit different anyways. So for any given theta, which is just an angle down in the xy plane, the angle that the rays, where I'm talking about the rays M that we already drew, the angle that the rays from part 2 make with the positive z-axis runs from phi equals the minimum value of phi to phi equals the maximum value of phi. So if you look at how the diagram has this drawn, you can see that the minimum value of phi is right here. So it's kind of the angle between this inner circle and the z-axis, and then we have the maximum value of phi is going to be the angle between this outer circle and the z-axis. And so we call that phi sub min and phi sub max. You could call it something different if you want, it doesn't really matter. But this phi sub min and the phi sub max are going to be the phi limits of integration. So you can think about, for all of these rays that I'm drawing up through my region D from the origin, the question is, what are the possible angles of those rays, or between those rays and the positive z-axis? And you want to find your minimum possible angle, that's going to be phi sub min, and then your maximum possible angle, which would be out along this circle in this case, and that'll be your phi sub max, and those will act as your phi limits of integration. And then finally, the last variable to worry about, we want to worry about theta. So we want to find the theta limits of integration. Well, in the diagram, the projection of our rays M down onto the xy plane give us this ray L, and theta can be thought of as the angle between the positive x-axis and that projection ray L. So as M changes, L is also going to change because L is the projection of M onto the xy axis. And L is going to sweep out that region R in the plane. So again, theta represents the angle between that projection ray L and the positive x-axis. And in the case of the diagram that we have above, theta is going to be bounded below by alpha here, and it's going to be bounded above by beta. So this ray out here. So you're kind of looking at the, if you look at the way that L is sweeping out this region, you're looking for when that angle between L and the x-axis is going to be smallest and when it's going to be biggest, and that will give you your limits of integration for theta. So after we've done that work, after we found the limits of integration, then we can say that the triple integral of f of rho phi theta over the region D is equal to the following iterated integral. So we have the integral from alpha to beta, of the integral from phi min to phi max, of the integral from g sub 1 of phi theta to g sub 2 of phi theta. So these are functions giving values of rho, of f of rho phi theta. And then again, we have to make sure we add in this times rho squared times sine phi, d rho, d phi, d theta. So that's the way to represent your triple integral as an iterated integral in spherical coordinates. Okay, now finally, the last task for the video is to give an example where we use spherical coordinates and integrate. So let's say we want to find the volume of the region D in space that's cut from the solid sphere rho is less than or equal to 1 by the cone phi is equal to pi over 3. So that sphere, rho is less than or equal to 1, is going to be a sphere centered at the origin of radius 1, and again it's solid, which means that it's filled in. And then we have the cone given by phi equals pi over 3. So each of these rays on the cone here, or maybe I should say the surface of the cone, if you look at any ray that's on the surface of that cone, the angle between that ray and the z-axis, the positive z-axis, is going to be pi over 3. That's what it means to have a cone described by phi equals pi over 3. So instead of sketching, again, this is a sketch that's not too difficult to do. You could probably sketch this yourself on homework. I didn't want to sketch it just because if you're just learning about a subject, I don't want my drawing skills to get in the way of your comprehension. So I just took the picture from the book, but you should be able to draw this kind of thing just freehand to get enough of an idea to be able to find the limits of integration. So after we have our sketch here, then we move on to finding the limits of integration. So notice that that rho is going to enter our region D at rho equals 0. So if we just take any ray M starting at the origin and we go up through our region D, notice that the moment we start, we're already going to be inside of our region because we're starting at 0 and or at the origin, and our region is touching the origin. So the lower bound is going to be rho equals 0, and the upper bound is going to be rho equals 1 because all of our rays exit the region when rho is equal to 1. So our limits of integration for rho, we're going to have rho equals 0 as the lower limit and rho equals 1 as the upper limit. Now notice that for each theta, phi is going to vary from 0 to pi over 3. So if, again, we just look at our ray M here, the question is, what is the minimum angle between M and the positive z-axis, and what is the maximum angle between M and the positive z-axis? So the angle between the ray M and the positive z-axis is going to be phi. And we can see that the ray can go all the way up to the z-axis and still be inside of the region. So phi min is going to be 0, but the ray can only go out to here. And the angle between this ray and the positive z-axis is still going to be pi over 3. So the maximum value of phi is going to be pi over 3. And that allows us to say that the limits of integration for phi are phi equals 0 as the lower limit and phi equals pi over 3 as the upper limit. And then finally, we need our limits of integration for theta. So you can just say that, oh, well, theta is traveling all the way around the z-axis. And because that's happening, we have that theta goes from 0 to 2 pi. So the limits of integration for theta will be theta equals 0 as the lower limit and theta equals 2 pi as the upper limit. And now we can move into the calculation. So the volume is equal to the triple integral of dV over the region D, which is equal to the integral from 0 to 2 pi of the integral from 0 to pi over 3 of the integral from 0 to 1 of rho squared times sine phi d rho d phi d theta. So we evaluate the inner integral here with respect to rho, and we get 1/3 times rho cubed times sine phi evaluated from 0 to 1. And we can take 1 and plug it in for rho, and that'll give us this 1/3 sine phi here. And now we want to integrate the next inner integral with respect to phi. And we get a negative 1/3 times cosine of phi evaluated from 0 to pi over 3. If we put in pi over 3 for phi here, we get a 1/2, since cosine of pi over 3 is equal to 1/2. If we put in a 0, then cosine of 0 is equal to 1. And ultimately, this gives us a 1/6. So we're just left with the integral from 0 to 2 pi of 1/6 d theta. And that's 1/6 theta evaluated from 0 to 2 pi. So then we can plug in 2 pi for theta, and we get this value pi over 3. So the volume of our region D that's sketched up here is going to be equal to pi over 3 using integration in spherical coordinates. So again, as I already said, previously in the video, at the end of section 15.7, the book offers a really nice chart of conversions between the different coordinate systems that we've now introduced, the different formulas that are going to be important, and this should be a helpful resource for you when you're completing homework or working on quizzes or exams, so make sure to check that out.